Good day, gents. So you guys requested for me to put together a video on electric fields. I thought I'd do that by using a PDF document that is already on Moodle for you. This is actually Mrs. Kritzinger's PowerPoint that she saved as a PDF, and it's on Moodle. And I thought it would be a good resource to use to explain this section to you. So this is actually part of the electrostatic section, so you will find a PDF there, and it's probably a couple slides, about 10 slides into that document or PowerPoint. Okay, so obviously electric fields, like I just said, forms part of the electrostatic section, and we obviously need to keep that in mind because we've already actually looked at electrostatic force and involving charges and the force experienced between two charges, right? Because that is actually where electric fields are derived from. So let's get cracking. Electric fields, what exactly is it? Okay, so it's obviously going to be different to electrostatic force. Force is always measured in newtons. Electric fields is related to it, obviously, and the definition here is an electric field is the area around a charge in which another charge will experience an electrostatic force. So it is not too dissimilar to magnetic fields, because in magnetic fields forces are also experienced, and they are also imaginary lines that you find between magnets. So the difference here is obviously some magnets, it's charges that have electric fields around them, either on their own or when they are in close contact with each other. So that leads me to the next point, the electric field lines. An electrical field line is an imaginary line that indicates the direction and strength along which a positive test charge will move if it is placed at a specific point in the electric field. So they mention positive test charge, emphasis on positive, because that is a clue to the direction in which electric fields move. They go from positive to negative. So positive test charge will, in any electric field, will move away from the positive towards the negative. And that is exactly how electric fields work as well, from positive to negative. Okay, here are just some examples of what the electric fields look like, but there are nicer diagrams on the next slide. So let's move on to the next slide. Here we go. Electrical field around a positive point charge. So these are just the drawn in electric fields around this positive charge. Here's a negative charge. Notice how the field lines move away from the positive charge at right angles to the charge. And another point about these lines is that they never intersect. They never cross. Okay, this is going towards the negative charge. When we have two charges together, obviously they will go from positive to negative, as I've said. They're still meeting on the charge at right angles, because they move away and towards charges radially. Okay, the density of these field lines show the strength of the electric field. So these two charges, for example, although they are opposite charges, they have the same strength because of the density of the field line shown here. Here we have just another positive and negative test charge. Electrical field of two opposite charges with different magnitudes. So you can see the density around this negative charge is higher than the positive. Here are two like charges. The lines will not intersect here, they will repel each other, so they won't cross. You need to be able to draw these scenarios. Here we have another positive charge moving away, and it's going to be greater in magnitude in terms of strength compared to this one. Here we just have two two parallel plates that are oppositely charged with the field lines between them. It's important to note that the force experienced by a positive test charge between these two parallel plates will be the same anywhere between these two plates. Regardless of where it is, it will experience the same magnitude charge. Right. So now obviously, like most things in physics, there are calculations involved. And these involve electrical field strength calculations. So you guys are already familiar with some of these symbols because you use them in the electrostatic section when you were dealing with Coulomb's law and electrostatic forces and that. So not too much that is new here. We obviously have the charge, that is Q, measured in coulombs. This is the new one, electric field strength. And then we still have that same proportionality constant. We've got the charge, obviously, and the distance from the charge in meters. That's important. Okay. I want to explain how we get to this point. You don't need to know how we derive it. I just think it's nice for understanding's sake how we get to this formula. So this is a formula we use to calculate electric field strength. It is the force experienced per unit charge. The force experienced per unit charge. And that also actually explains why the unit in which electric fields are measured in is Newton per Coulomb. Because remember, force is measured in newtons and charge in coulombs. That's why it is Newton per Coulomb, as you can see down here. Alright, so this is the one. That's the one way we can calculate electric field strength. But remember, the electrostatic force is calculated using this formula over here. So if we combine these, if we substitute that part over there into that equation over there in the forces position, we get this, which will mean that the one charge, the one Q here is cancelled, which leaves us with this electric field strength formula measured in newtons per coulomb. Sorry about the typo there. Alright, so that explains how we get that, and that's what you guys are going to be using most of the time. Now here are a couple of questions. Calculate the electric field strength 0.1 meters from a point charge of 5 microcoulomb. Remember, you've always got to write your magnitudes in scientific notation. You don't write microcoulomb, you don't use that symbol in your calculation. You don't say 5, you say 5 times 10 to the power negative 6. Okay, so over here we have answers. You obviously use your formula, you substitute your values, you've got your constant, you have the magnitude of the charge, and you have the distance. It's got to be in meters, it's already given to us in meters, so that's sorted. This is written out in full. You can obviously also write it out in scientific notation with the necessary decimal places given. 16.2, calculate the electric field strength of 10 to the power negative 6 meters from an electron. Okay, just a bit of a change. Remember, we need to know what the charge of electron is, which you guys know from the previous section. And there we go, substitute the charge of the electron in there, that's the distance, and you work out the electric field strength. These are all fairly sort of basic questions. So the information is given to you, and all you're doing is you're substituting those values into this equation to find your unknown. Here they ask for the distance, so you work out the distance, that's your unknown. Here they ask for the charge. So there's just different ways of asking this and having a specific unknown which you need to work out. The questions I want to get to is really the net electric field. Okay, so here's a nice question on net electric field. Calculate the net electric field for each of the following charges at a point P 1 centimeter to the right of charge C. So here we have charges A, B, and C. They give us the distances here 0.2 centimeters, 0.4 centimeters. And then let's say there's another charge, there's another point P over here that's a centimeter away from charge C. So what we need to do now is we need to work out the electric field strength relative to every charge. So from A and from B and from C, all separately done, as you can see over here, the electric field strength from point A. So you are going to use the charge of A over there, and you're going to use the distance away from A to P over there. So if you work this out, 0,2 plus 0,4 is 0,6 centimeters plus another centimeter is 1,6 centimeters. And then you need to convert that to meters. That is why it is in 0,016. So 16, so 1,6 centimeters is 0,016 meters. And that's why every one of these examples are going to look different, because the charges are different for each charge, A, B, and C. Here we use B's charge. The distance from B to point P is going to be different when you work out the electric field strength. Notice there is direction, because electric field strength is a vector. There's always going to be magnitude and direction. And it's going to be to the right because these are positive charges. Those are positive. So electric fields move away from positive charges. That's why it's going to push whatever is here at P to the right. Hope that makes sense. This was a negative charge, charge C. So that's going to mean that the electric field relative to C is towards C. So that's why the electric field experienced by point P over here due to C is going to be to the left. But the question asked for the net electric field at this point relative to these charges. So you need to go and calculate the net electric field. You can pick your positive direction, which in this case was to the right, and your negative direction obviously be to the left. Sorry, this is not very clear. It's a plus, it's a minus. And then you get a negative answer, which means you need to basically interpret that with a direction, which in this case negative was left. Okay, there we go. And that is your final answer. And the unit being newtons per coulomb. Moving on to the next question. Two charges are positioned as shown in the diagram below. Here we have Q1 and Q2. This is positive 8 microcoulombs and negative 2 microcoulombs. The question is, find the magnitude and direction of the electric field at A. So again, this is a net electric field at A relative to charge 1 and charge 2. Here are the distances in meters already. They're given us the charges, so it's not that difficult. Calculate the electric field strength due to Q1. That's 8 times 10 to the power negative 6. And the distance is 6 meters, which is 4 plus 2. And you get your answer there. It's to the right because that's positive. So it's going to have to move away from this positive charge to the right. This is now negative, so it's going to move towards the negative. And here we go. Substitute your values and you get this answer. You still need to calculate the net electric field, and that it is over there. Just want to quickly go back to the original. Okay, we've done that. Here's the next question. Use the information in the following diagram and calculate the net electric field strength at point P. Interesting, because now, okay, probably not shown here, but you should know that this is a 90-degree angle, so they are perpendicular to each other. This is similar to what you guys have seen in forces, in the forces section, because forces also have magnitude and direction. Okay, so let's have a look at the answer. So now you will calculate the electric field strength based on Q1, and that is going to be towards Q1 because it is a negative charge, so it's going to be to the right. This one is going to be away from this charge over here, Q2, because it's positive, so it's going to be up. So we've got up and to the right. So how do we calculate the magnitude of the electric field? It's going to have to be by means of Pythagoras. Sorry, there's a clearer diagram of what's going on here. But here we go. Pythagoras, E1 squared plus E2 squared, 9,000 squared plus 7,200 squared. So it's basically these answers. that you're substituting in here to get the hypotenuse. And then you add this together, square root it, and we get our value over here. What we didn't do though is calculate the direction, the bearing, which is something that you would have to do because they didn't ask just for magnitude only, they asked for the net electric field strength, not the magnitude of the net electric field strength. So you still actually have to calculate the bearing, which we're not going to do at this stage. But you guys should know how to do that by now because we've done that in the forces section as well. Okay, and then coming back to this PDF document here, electric field strength at a point in the electric field. We've already looked at this formula as I showed you previously, how we derived this other equation. This is actually just an example of the type of question we can get when we don't have to use the other formula, where we use this formula. Charged object experiences a force of 8 times 10 to the power negative 3 newtons when it's placed in an electric field with a strength of 1.6 times 10 to the power 6 newtons per coulomb. Calculate the magnitude of the charge on the charged object. Okay, so we've got force, we've got electric field strength, so we can calculate charge by substituting those values into this equation, and you can see that in this model answer over here, substituted in there. Okay, sorry, no, this is a different question, my bad, but just an example of how we can do this using this formula. So all the information is already given. Alright, gentlemen, I hope and trust that this has helped you and will be of assistance with regards to electric field strength. I just think the most important part in this section is to understand that electric field strength is a vector. We calculate it using E equals K times Q over R squared, and a question, sort of the higher level question in this section, is working out the net electric field strength, where there's more than one charge affecting a certain point charge, and you need to now work out the net electric field at that specific point. Always remember that electric fields move from positive to negative, so it's going to move away from the positive and towards the negative. That is what you need to remember. And when you calculate your net electric field strength, you then obviously decide which direction is your positive and which is your negative, so that you can get the correct net electric field strength when you add those values together. And then the final answer will also have a direction. Right. So I hope this was helpful to you. Please let me know what you think by writing in the comment section, or send me a private message. Really is up to you. All the best, guys. To the next lesson.